Welcome, and thank you for joining the WindSim Power Forecasting webinar today. Matteo Mano, who is on the development team behind this technology, Dr. Catherine Meisner, who is the manager of the development team at WindSim, and I, Donna Renimo, who is working with the channels and the market alliances, will discuss how WindSim is providing cutting-edge forecasting models of wind power. Today, we envision the presentation to last 40 minutes. And we then will open up the floor for questions and answers thereafter as necessary. All of you that are participating are muted to enhance this presentation. Questions can be sent in via the chat window to the WebEx host, and we'll address as many of these after the presentation. Otherwise, we will follow up with an email. So before we go and talk about forecasting models, well, let's talk about market forecast. So before the power forecasting, let's talk about the market forecast. GWEC, the Global Wind Energy Council, released their annual report this month and discussed its findings on a press call. Even though the major wind markets of the past few years have slowed, overall global growth of wind energy will remain solid for the foreseeable future. That's good news for all of us in this industry. The chart shows the market forecast for 2014 to 2018. Note that by the end of 2018, GWEC predicts that there will be just about 600 gigawatts of installed wind power capacity, almost doubling where the industry is today. So you see here, see where we're starting from here. The 2013 market saw China back on top, installing about 5 times as much wind power as Germany, who is in the number 2 spot. USA, who was a 2012 market leader, dropped back to 6th place due to the drop in the US market by about 3 gigawatts. But because of the nature of the PTC reauthorization and the strong pipeline of new projects, GWEC expects USA to make up that 3 gigawatts in 2014. Canada and Brazil had a record year in 2013, and despite a lackluster year, India moved into 4th place, right behind the UK, which had a good year both on and offshore. 2014 looks to be a record year with annual market growth of about 33%, to bring the annual market to about 47 gigawatts, with strong installations in North America and Asia, and the Brazilian market really beginning to come into its own. Brazil, Mexico, and South Africa will figure increasingly strongly in the annual market figures in the years to come. After 2014, as you can see on the chart, they are expecting the market to return to a more normal annual market growth rate of between 6 and 10% out to 2018. Last week, we saw an article in Bloomberg Business Week that stated that the surge in Texas wind generation is pulling down spot power prices. Today, we see wind driving the energy market in Texas. By providing the utilities with an enhanced 24 to 48-hour forecast from the variable generation assets, the energy market will benefit overall. So let's take a look at the benefits of our solution. Asset owners, portfolio managers will benefit operationally through the implementation of the WindSim Power Forecasting System. The CFD, or Computational Fluid Dynamics-based power forecasting solution, especially adds value through improved forecast accuracy in wind park locations that include complex terrain. Accurate power forecasts enable control over revenue and cash flow and have a direct impact on the bottom line. By providing customers with a better forecasting system and enabling the implementation within their day-to-day operating systems, this solution will help them to reduce their need of balancing their wind power. There are several challenges associated for wind power producers participating in electricity pools, due to wind power forecasts containing an inherent part of uncertainty. There will always be regulation costs induced by forecasting errors. WindSim's objective is to improve the level of accuracy by developing our power forecasting solution through the use of our wind energy and CFD expertise, so we can help increase the market value of the wind power forecasts overall. This slide shows an example from one of the grid operators in Germany called TenneT. It demonstrates that wind power production output is very unstable and challenging to predict. And I guess that's not new news to most of you on this call. This slide demonstrates that the distribution of imbalance can be very volatile. The imbalance being the absolute difference between the forecast and the actual production divided by the actual production. We're seeing outliers sometimes more than 900%, as you can see here. And just briefly, a bit of a background. The regulation market, which is managed by the TSO, or the transmission system operator, ensures the real-time balance between generation and load. Even if the settlement mechanism for imbalance prices varies from one country to the other, the general principles remain the same. In the case for which production perfectly matches consumption, no regulation is needed. If production is not sufficient to meet the load, this leads to an up-regulation situation for which it is necessary to increase generation or decrease consumption. And if production exceeds consumption, one faces a down-regulation situation where generation has to be reduced. And if the grid has good interconnection with neighboring systems, a part of the excess energy may be exported. But more often, generation curtailment is envisaged for lowering generation, which I think all of us will agree is quite a shame to have to curtail the wind. So WindSim is one of the first companies to implement CFD, computational fluid dynamics, as an integral part of a comprehensive and commercial wind power forecasting solution. CFD allows us to downscale the mesoscale weather predictions to the resolution necessary to describe the wind flow inside a wind farm. There are many blind tests that have been conducted over the years that have demonstrated the superiority of CFD compared to other methods. So let us talk to you about the WindSim solution. Dr. Meisner will now demonstrate our capabilities, and give me one moment and I'm going to turn this presentation over to Dr. Meisner.
Thank you, Donna, for this nice introduction. Hello, everybody. I will give you now an overview of our WindSim power forecasting tool, which can be used to downscale the mesoscale numerical weather prediction forecasts of wind speed and wind direction to every turbine position and to calculate the power production at every turbine. For this downscaling procedure, we combined artificial neural networks for correcting the mesoscale forecast, computational fluid dynamics for the three-dimensional flow modeling inside the wind farm, weight modeling to correctly predict the power production of the individual turbine, and empirical power curves to give more realistic power production. During this webinar, I will explain each technique and how they can be combined. All common numerical weather prediction output formats can be handled in our software. First of all, how do we couple mesoscale and CFD? The first thing we use are global models. They have a resolution of 100 down to 16 kilometers. Here we take, for example, the GFS or the ECMWF solution. Then we go down to the regional models. They have usually a resolution of 9 to 1 kilometer for the description of the atmospheric conditions. After the regional models, we can then run the micro model, which is on a resolution from 100 down to 10 meters. And here we get the accurate description of the local flow fields and the weight effect. I just want to show this added value of using CFD with some pictures. On the left-hand side, you see the best resolution possible in mesoscale models today. It's around 500 meters. And on the right-hand side, you can see the resolution you can get in a microscale model. So in WindSim, this goes normally down to 20-meter resolution. And you can see already here that the terrain is much better described in the mesoscale, in the microscale model. When we then look at the wind field, then we can see a clear difference between the mesoscale model and the micro model. The micro model can describe much more in detail the flow field around the turbines, which are presented in gray here. When we then think of the rate calculation, which is really important to give you really the exact power on the turbine position, then the weight calculation is also much more accurately done in the WindSim model or in the microscale model, because it's a much higher resolution than the mesoscale model. How do we couple the mesoscale and the CFD? We do this by a so-called virtual net mass solution. This means we take 1 point from the mesoscale model and transfer it inside the CFD domain. And then we use the CFD model to scale the results to every turbine position. The advantage is that this is a very fast approach, because we can produce so-called CFD lookup tables already in the setup phase, and then during the forecasting system is running, there's no CFD simulation necessary anymore. For today, a direct coupling of numerical weather prediction models to the CFD solution is still too time consuming. So what do we do in the coupling phase? So we take the mesoscale weather prediction model results, we take 1 point and we transfer this inside the wind farm. This we do by so-called artificial neural network solutions. Then out from the prediction which we have gotten on 1 point inside the wind farm, we are able, with the help of the CFD, to transfer this to each individual turbine position, such that we get individual wind speeds for every turbine. Why do we need the artificial neural networks? It is well known that the mesoscale models have often phase and model bias errors in wind speed and direction. I want to illustrate this on a graph. You can see the wind speed over 2 months in a year, and in green we have the raw mesoscale data, and in red we have the measurements on the side. And here we can see clearly the bias between the model and the measurements, and you can also see some phase shift between the model and the measurements. And if we apply the artificial neural networks, we have then the possibility to correct this error, and you can see the corrected mesoscale data in blue here, which fits much better to the observed measurements. So how does the basic forecasting application in WindSim look like? We have a setup period on the left-hand side and a forecasting mode on the right-hand side. And in orange, you can see all inputs we need to give to the system. As shown before, we need first the global forecast and then the mesoscale forecast to give it to the model. And during the setup period, we need so-called mesoscale hindcast. These are numerical weather prediction model results, which are run for past periods. And then for the same time period, we also need historical wind measurements. With these two data sets, we can train the artificial neural networks. And then also in the setup period, we prepare the CFD lookup tables. This means we really run the CFD model on the side. After we have obtained the setup period, we can then in the forecasting mode take the mesoscale forecasts and put them through the neural network correction into the CFD. And in the CFD model, we can apply the weight modeling at every turbine position. Then in the end, we get out the power production forecast. I want to demonstrate our basic forecasting application on a showcase. It's Hundammer. This is a place situated in the north of Norway. And you can see on the upper left side the mesoscale model results here colored. And then you see the single grid points of the mesoscale model displayed on the map below. We have then picked the closest point to the wind farm and run a forecasting with this. From the mesoscale model, we get the so-called grid file, which contains the time series of horizontal wind speed components and the wind direction. We have gotten the forecast in a 3-hourly time stack, and we are doing an 8 days ahead forecast. Before we can go into the forecasting application, we first have to set up the WindSim model and to run it through different steps. First, we set up the terrain for the model. Then we run the wind field simulations, normally for 12 to 36 sectors. And then we place the objects module, where we place our turbines in every location and also place one climatology point. So this means this is the point where we want to scale our mesoscale results to, and where we normally would expect to have measurements inside the wind farm. After we have set up the model, we can go inside the forecasting application, and here we have to do several steps to obtain a solution. The first step is that we train the neural network. On the right-hand side, you can always in the application see the settings. So we give our input data, which is necessary, so the hindcast data, we give the historical measurement data, and then we also give some settings for the neural network training. On the left-hand side, we can then observe the progress of the solution and control that we got a good training. And we also get some information about the training. After the training step, we can control once more that all the objects are placed in the right position, and we can do some settings for the energy calculation, for example, air density correction or the weight model we want to use. After we have done this, we can finally start the actual forecast. And here you have the possibility to download the actual forecast from, for example, FTP servers or also from local folders. This means when you once have started this application, it will go to the FTP folder, and every time your Mesoscale data provider gives you a new forecast, we will download this forecast automatically and issue a new forecast, which you then can see here in the graph on the left-hand side. The blue line is the current time, and then in red you can see the estimated production. Beside of this graph, you can of course also get it as a file format, so you get for every single forecast time series where you can see the single production of the turbine, and then in the end also the summation for all the turbines. These files you can then take and post-process in your own application. So when we switch back to the presentation, then I want to show this once more, because the most important thing for the artificial neural network is really to have the good historical wind measurements and good mesoscale hindcasts. I want to explain a bit what the neural network is doing. So the neural network is learning on the data which we provide to it. So we provide a time series for the past time from the numerical weather prediction model and from the measurement. On the past, we train the system, and then we are able to predict it in the future. So after we've trained the neural network and the new numerical weather prediction forecast comes in, we can do the correction, and then we get actually wind speed and wind direction inside the wind farm. Important for the system is that the data is cleaned before we do the training, because if the cleaning is not done in a good way, then this can lead to errors in the correction. I want to show now a validation of the system, which we have done, obtained from a customer in Italy, Studio Rinnovabili. They have run the forecasting on 4 sample sites using the artificial neural networks, and the performance is depending on the complexity of the terrain. When we look onto the table, then I want to draw your attention to the last column, because here, displayed is the normalized mean absolute error, which is the most common error measurement in the industry. What we can see here is that for the first site, MCAM, which is a really complex site, so all the green stars are complex sites. We have applied the system and we have done an artificial neural network correction before we run the power forecasting with the CFD. If we use instead of the artificial neural network a common measure correlation predict method, then we can see that the error is 2% higher. This gives us a certainty that our artificial neural network solution gives a good correction of the mesoscale data. When we look further towards the PNP side, then we can see that we obtain quite low error if we use a MetMask, a second MetMask as a forecasting. This means we have one MetMask where we can train the system, and then we use instead of the mesoscale forecast, we use a second MetMask as input. This means that our forecast has not really an error, but the 2% come then due to the conversion from the measurement point to the single turbine. So this means that the CFD solution is working quite well and giving reliable results. What is also important to notice is that the highest errors really come on the most complex sites, here signed with green stars, and we get better results in the sites with medium complex terrain. The error range of the normalized mean absolute error is in the range of the industry standard today. Besides of the forecasting application which you can buy from us per today, we also offer some add-on capabilities. If you can use to improve your system, so if you have your own power forecasting system already built up and you want to use our solution, then you can improve this by using our add-on capabilities. We have developed empirical power curves, artificial neural networks power, online data from MetMask, so-called online wind, and online data from SCADA, so-called online power, which I will now explain in detail. In the normal WindSim forecasting, we use the normal power curve from the manufacturer to get from the wind speed at the turbine position to the power production of the complete part. This is a good first assumption, but we know that nominal power curves are measured on flat terrain, and in complex terrain they might not hold true anymore. If we have access to SCADA data, we can therefore create an empirical power curve and use this to predict the total power of the part. If we look at a comparison between the nominal power curve and the empirical power curve, then we can see here that we have a huge difference in the power curves, especially in high wind speeds. Here the nominal power curve in orange and the empirical power curve in red. But we also get a considerable difference between the two solutions for the ramp inside the power curve. To get to an empirical power curve, we have to get access to the SCADA data. We are cleaning the SCADA data, and then we relate the energy production to the measured wind speed on the site. We can do this for the complete 360 degrees, or we can also split this per sector. As you can see here, we have the sector from north or also from northeast. And sometimes this can really improve the system because we have wake effects in the turbine for some sectors. So to have empirical power curves for different sectors might improve the system. Then we can also provide empirical power curves per season. This might also be quite useful if you have icing on the site. So how does the system look with the empirical power curves? We have first the basic WindSim, as I presented it before. And then we can, if we have access to historical wind measurements and historical power production, we can create empirical power curves, which are then used to do the actual power production forecast. the NMAE is decreasing thereby by 1.5%. Another add-on capability which we provide is the ANN power-to-power. This means that after we have calculated the power production from the complete wind farm based on CFD results, we can run another neural network which is correcting the power output. We can do this for the complete wind farm, or we can also train a neural network for every single turbine. What would we do to obtain the solution? We would run the normal WindSim system down to the power production forecast for historical time periods. And then we would take the power production forecast, which we obtain here for historical time periods, and train the neural network together with the historical power production. This means that then when we actually come into the forecast mode and do an actual forecast, we correct the power production forecast, which comes from the CFD, again with an artificial neural network, and we get again a power production forecast. By using this technique, we can decrease the NMAE by 0.5 to 2.5%. The third add-on capability which we have is the online data from the MetMast. So normally when we take the mesoscale data from the one point and put it into our system, we will run an artificial neural network correction. This correction we can improve if we have real-time access to wind measurements inside the wind farm. And then we will also give out again the power in the end. The NMAE decreases around 2.5% in the first hours. So this is really a suitable system for short-term forecast. This will always be improved by having real-time data from the site into our system. The same we can then do for the power. So if we have online access to SCADA data and we can in real time feed the online data into our system, we can run another artificial neural network to decrease the NMAE even further. Here we find also around 2.5% improvement in the first hour. And then, of course, we can make the magic system where we then have the online data for the wind and the online data for the power together and able to improve the system even more. So if we have look again, an overview over the complete system, we have the setup period, which has become much more complex for the complete system. If we have access to historical power production, then we can really improve, because we can have empirical power curves and we can use a neural network for the power correction. And we have also new data which we can place into the system if it's available, online data for the wind and online data for the production. What is the added value of the CFD in the forecasting? On the top, you can see the normal forecasting procedure as many people use it today. We get the mesoscale wind speed from a mesoscale model. We do a model output statistic or an artificial neural network. And then we have statistics based on historical production. And out from this, we get usually an energy production forecast for the complete park. With WindSim, you can go a bit a different way. We start in the same way until the artificial neural network, but then we set a deterministic tool below. So we really do a flow field calculation. We run analytical wake models, and then we issue an energy production forecast for every turbine and also for the complete park. What is the advantage? A deterministic tool is able to catch the extremes. Statistical tools are often known to be good in average, but they smooth the extremes. We can really downscale the NWP forecast model to a resolution which is necessary to describe the wind flow inside the farm. We can do weight calculations, which are normally not possible on statistical methods. And the good thing, and really the important thing compared to statistical methods, we can run without SCADA data to go down to the production. And we can calculate the production per every single turbine. With this slide, I want to close and give the word back to Donna Rinnovabili.
Thank you very much, Dr. Meissner. Let's see. Share my desktop here. One moment. Catherine, having a problem getting back to my desktop here. Do you want to just put your desktop back on and we'll just step through the slides?
Swap now. You should be able to swap now. Try again.
Okay, yeah. There we go. Sorry about that. So let's talk about the implementation alternatives. Everyone that is interested in this solution, it is sold at, you need to have WindSim, the core technology, and then it's sold as an add-on module, as we sell our other add-on modules today, the Park Optimizer, remote sensing correction. In tandem with that is consulting time that's required to set everyone up. So that initial investment today looks about $10,000. Now, as Dr. Meissner has stated, we have add-on capabilities that are priced separately, and those include the empirical power curve, the ANN power-to-power, the online data for mass and SCADA data. These are all priced separately, and it depends on your park and what you want to accomplish, and we welcome the opportunity to talk to you further about that. Different ways that we are working with customers today also include collaboration and customer-tailored solutions. So, enabling us to create quality in all steps related to the wind power forecasting. We have various users of our wind power forecast solution today. They include the independent system operators, the transmission system operators, generation companies, wind power producers, utilities, wind farm owners, analysts and traders, power system, electricity market operators, and companies providing forecasting systems and services. We have various alliance partnerships that we are involved in working with, and this enables our company to move this technology forward and together provide a better solution to industry. So some of these relationships are noted on the screen. We've been working and developing tools for a company called Aquilos. We've done various research projects with Uni Research. We're running some testing and forecasting initiatives with the companies you see there. And then a partnership with University of Technology, Shenyang in Asia. And at this point, I would open up and say to all of you, we welcome the opportunity to talk to any of you about alliance partnerships and the potential to move forward and do pilot initiatives as they make sense. Another exciting alliance partnership we would like to introduce to you is our cooperation with the United States Department of Energy's Idaho National Laboratory. They are supported by DOE's Wind and Water Power Technologies Office, and we are today working in tandem with Idaho Power. We are working together on an applied R&D project that focuses on increasing transmission capacities with dynamic monitoring systems. So just a little bit about with this project. Transmission line ampacity ratings, traditionally limited by conductor thermal capacity, are defined by a static rating using predetermined environmental conditions. Without accurately measuring environmental conditions and their effects, existing transmission lines can be critically underutilized. Using a dynamic line rating system to accurately monitor these conditions leads to improved line ampacity ratings and the safer operation of the overall electric grid. Renewable power production stands to directly and most immediately benefit from increased transmission capacity through improved weather-based dynamic line rating systems. The INL system being developed, tested, and implemented improves overall dynamic line rating quality and leads to average capacity improvements of 10 to 40%, and even more in certain areas. So we are also, the Idaho National Laboratory and WindSim are interested in talking to potential partners about them participating in this program with us. You can find ourselves and Idaho National Laboratory at AWEA next week in Las Vegas. We will be jointly talking further about this opportunity. And again, we welcome any of you who's going to be at that show to talk to us, as well as WindSim will be talking, of course, about our other solutions that we sell and offer to industry. We will also, with the Idaho National Laboratory, be presenting at UVIG later in the month in Anchorage, Alaska. So with that, I thank you very much for attending today. And if we have some time here, let's see, we still have a bit of time. We can take a couple questions. Any of you can send those in via the chat window. Catherine, I believe that you have some. Would you like to start, or do you want me to read them?